everyone, thanks so much for joining me for this lesson. Today we're going to be learning about the equilibrium constant Kp for homogeneous systems. And so these are our learning objectives. The first is to define what Kp is, and then we're going to also define partial pressure and mole fraction. So at the end we should be able to derive partial pressure from mole fraction and total pressure, construct an expression for Kp for a homogeneous system in equilibrium, perform calculations involving Kp, predict the quantitative effects of changes in temperature and pressure on the position of equilibrium, to predict the quantitative effects of changes in temperature on the value of Kp, and finally to understand that whilst a catalyst can affect the rate of attainment of an equilibrium, it does not affect the value of the equilibrium constant. Kp is the equilibrium constant, and it's the equilibrium constant for gases. So many reversible reactions take place in the gas phase, and gaseous equilibria also obey the equilibrium law, but it's usual to express their concentrations in a different way. Instead of having the equilibrium moles and then the concentrations, we have partial pressure instead. So Kp is defined to be the fraction of the partial pressures of the products over the partial pressures of the reactants. So this small p here stands for partial pressure. And so Kp is the equilibrium constant calculated from partial pressures for a system at constant temperature. We're now going to define partial pressure and mole fraction. So partial pressure is the amount of pressure that a specific gas contributes to the total pressure. So it's the pressure that the gas would exert if it occupied the container on its own. So the partial pressure of A would be the amount of pressure that this gas A contributes to the total pressure, so the fraction of it. And the mole fraction is the number of moles of that specific gas divided by the total number of moles of gas in the entire mixture. So therefore, we can form the equation of partial pressure, which is denoted by a small p, is equal to the mole fraction times by the total pressure of the entire mixture. At the top, we have the general form of an equation. So the small letters, they are how many moles we have of the different things. So these are the moles, and these big letters are the species. So for example, we could have carbon dioxide or something as a species, and moles would be the number in front, and this is the same with the other side. And so we can form an expression for Kp. So Kp is equal to the partial pressure of the species X at equilibrium by the power of how many moles we have of it, and then multiplied by the partial pressure of the species Y at equilibrium by the power of how many moles we have of Y, and then multiplied by the partial pressure of Z at equilibrium by the power of how many moles of Z we have. And this is all divided by partial pressure of the species A at equilibrium by the power of how many moles we have of A, multiplied by the partial pressure of B at equilibrium by the power of how many moles we have of that, and then multiplied by the partial pressure of C at equilibrium by the power of how many moles of C we have. Now we're going to look at how to find the mole fractions and partial pressures. So first of all, if you've forgotten how to calculate equilibrium moles, then I'd suggest you quickly look back at the KC videos and find out how to calculate the equilibrium moles before you come back to this video. So after finding the equilibrium moles of all the gases, we use these two equations below to help us find the mole fractions and partial pressures. So first we have the mole fraction of A is equal to the moles of A divided by the total moles of the gas. And the second equation is the partial pressure of A is equal to this mole fraction of A multiplied by the total pressure. A really important note is that the sum of all mole fractions equals 1, and that's because they're all fractions of the total moles of gas, so they have to equal 1. So now we're going to move on to this example. Find the mole fractions and partial pressures of all the gases in this reaction, and the total pressure is given to us as 255 kilopascals. So the first thing we do is work out the mole fractions. And for example, the mole fraction of CH4 would be the moles of CH4 divided by the total moles of gas. And so because we have all the equilibrium moles here, we can actually find out the total moles of gas by adding them all up together. So at the side, you can write total moles of gas, and that equals 0.8 plus 0.8 plus 1.2 plus 3.6. And that gives us 6.40 moles of gas. And so now we can work out the mole fractions. So we have 0.80 divided by 6.40, and that gives us 0.125. And then here we have the same thing. And then here we have 1.20 over 6.40, which equals 0.1875. And then this last one is 3.60 over 6.40, and that equals 0.5625. And so here we have our mole fractions. So now we can work out the partial pressures because they've given us the total pressure here. And so we do the mole fraction times by the total pressure. So we have 0.125 times by 255, and that equals 31.9 kilopascals. Then here we have the same thing, so 0.125 times 255 equals 31.9 kilopascals. And then here we have 0.1875 times by 255, which equals 47.8 kilopascals. And then here we have 0.5625 times 255, which equals 143 kilopascals. And here we have our partial pressures. And I rounded all these to 3 significant figures because this pressure is given to us in 3 significant figures, and also these initial moles that they've given us are also in 3 significant figures. Now we're going to work out the Kp. So for this example, find the value for Kp using these partial pressures. So CH4 is 31.9 kilopascals, water is 31.9 kilopascals, carbon monoxide is 47.8 kilopascals, and hydrogen is 143 kilopascals. So here we have the equation, and now we're going to work out the Kp. So we write out the expression for Kp. So Kp is equal to the partial pressures of the products divided by the partial pressures of the reactants. And so we have the partial pressure of carbon monoxide multiplied by the partial pressure of the hydrogens. And this will be to the power of 3 because we've got 3 moles of hydrogen. And then this is divided by the partial pressure of CH4, and then multiplied by the partial pressure of water. And then this gives us so now we plug in the numbers. So we get 47.8 times by 143 cubed all over 31.9 times 31.9. And this gives us 137,000. And now we need to work out the units of Kp. So like Kc, we write down all the units and then cancel. So on the top, we have a kilopascal for the carbon monoxide, and then we have kilopascal cubed for the hydrogens, and then on the bottom, we have 2 kilopascals. And now we can cancel. So we can cancel this and this, and we're left with kilopascals cubed over kilopascals on the bottom. So that equals kilopascals squared. So the units are kilopascal squared. So there are three very important things to remember about Kp. And the first is that it's only affected by temperature and pressure. So when we alter the concentration, then it isn't affected. So the Kp stays as the same value. The second is that we can predict the qualitative effects of changes in temperature on the value of Kp. And then for number three, a catalyst has no effect on the Kp. Please note that increasing the pressure or temperature on a gas phase reaction will increase the rate at which equilibrium is reached. So, explaining in more detail, for number one, for example, if we had the Haber process, so we've got 3 hydrogens and that's added with a nitrogen to form 2 ammonias. This is an exothermic reaction, so it has a negative enthalpy change of minus 92 kilojoules per mole. So if we increase the temperature of this, then by Le Chatelier's principle, the equilibrium would shift to lower the temperature, and it would favour the endothermic reaction because that takes away the heat energy. And so it would favour the reactants, the back reaction, if we increase the temperature. So looking at Kc, so looking at Kp is equal to the partial pressure of the ammonia squared over the partial pressure of hydrogen cubed multiplied by the partial pressure of nitrogen. So if the equilibrium has favoured the back reaction, that means that the bottom of the fraction will be a lot bigger than the top, and so Kp will be quite small. So if we increase the temperature, then Kp will be small. And the opposite of that is true as well. So if we decrease the temperature, then the equilibrium will shift to increase the temperature by Chatelier's principle. And so it'll favour the exothermic reaction because that gives off heat energy, and so favours the forward reaction, so it shifts to the right. And so we get more products, so we get a bigger value on top of the fraction for Kp compared to the bottom, and so the Kp is big. So when we decrease the temperature, the Kp is big. And now when we look at pressure, first we count up how many moles of gas we have on each side. So on the left we have 4 moles, and on the right we have 2 moles. And so that means that when we increase the pressure, because the equilibrium shifts to decrease the pressure, it favours the side with the least moles. So that means it shifts to the right, so it favours the forward reaction. And so we get more product, so there'll be a bigger value on top of the fraction for Kp, so Kp is big. So if we increase the pressure, then we have Kp as a big value. And then when we decrease the pressure, the equilibrium shifts to increase the pressure. So it favours the side with the more gas molecules, which is the left-hand side. And so the equilibrium shifts to the left. And so there are more products, so the bottom of the fraction for Kp is bigger, and so Kp is small. So we have that when we decrease the pressure, then we have a small Kp value. And so this also explains number 2 about the temperature. And then for number 3, a catalyst has no effect on the Kp, and that's because a catalyst just speeds up the reaction. So it speeds up the forward reaction and the back reaction by the same amount, and so they cancel out, so overall it has no effect on the Kp. Now we're going to have a look at some questions. So give the units of Kp in each case. So we're going to start off with A. And we know that Kp is the partial pressure of the products, divided by the partial pressures of the reactants. And so we can find out the units quite easily by just writing out the units of each of the species and then cancelling out. So we have the SO3. So let's just say that everything is measured in pascals. So we have a pascal for the SO3. And this is squared because we've got 2 moles of it. And then we have an oxygen, so that's just 1 pascal, and then multiply it by the partial pressure of the SO2, so that'll be pascal squared again because we've got 2 moles of SO2. And so we can cancel out the pascal squared, so we get 1 over pascal, which is pascal to the -1. So that's the units for A. And then for B, we do the same thing. So we have the water multiplied by the carbon monoxide, and then over a hydrogen multiplied by carbon dioxide. And as you can see, everything cancels out, so there are no units. And then for C, we have the NO2, which is pascal squared, and then over the N2O4, which is pascal. So the units for the Kp is pascal. So before I get started with number 2, feel free to pause the video and to try it out yourself first. So in the below expression, what would happen to Kp if the temperature would decrease, more of A was added to the mixture, and a catalyst was added? And so first, let's write down our expression for Kp. So for this, our expression for Kp would be equal to the partial pressure of C multiplied by the partial pressure of D over the partial pressure of A multiplied by the partial pressure of B. So then for A, if the temperature would decrease, the equilibrium would move to increase the temperature, and so it would favour the exothermic reaction. Now we can see from this delta H here that the forward reaction is endothermic, and so if the temperature would decrease, then we would favour the exothermic reaction, which would be the back reaction. And so the equilibrium shifts to the left, and so more reactants are formed. And because there are more reactants formed, that means that the bottom of the fraction for Kp is bigger, and so Kp decreases. And then for B, if more of A was added to the mixture. Now, the really important thing to remember about Kp is that only 2 things can change the value of it, and that's either the temperature or the pressure. And adding more A means that we're increasing the concentration of A, and so that means that it doesn't change. Hi everyone, thanks so much for joining this video. We're going to look at some harder questions for the topic of Kp. So number 1 says that a sealed flask containing gases X and Y in the mole ratio 1:3 was maintained at 600 Kelvin until the following equilibrium was established. The partial pressure of Z in the equilibrium mixture was 6 megapascals when the total pressure was 22 megapascals. For A, write an expression for the equilibrium constant Kp for this reaction. So for A, we know that Kp is equal to the partial pressures of the products over the partial pressures of the reactants. And so the expression is the partial pressure of Z, which is squared because there's 2 moles of Z, and then divided by the partial pressure of X multiplied by the partial pressure of Y cubed because there's 3 moles of Y. And so that's our answer for A. And then for B, calculate the partial pressure of X and the partial pressure of Y in the equilibrium mixture. Okay, so first of all, I'm going to start off with writing out the equation again. Now, it's actually a lot easier than it looks because firstly, you might think that you need to work out the equilibrium moles and the mole fractions in order to get the partial pressure, but actually we can just look at the ratio. And so we're told that the partial pressure of Z in the equilibrium mixture was 6 megapascals. So we've got 6 megapascals of the Z, and this is the partial pressure. And we know that initially the mole ratio was 1 to 3 between X and Y. And so from that, we know that in the mixture at the beginning, a quarter of it was X and 3/4 of it was Y. And from that, we can actually work out their partial pressures. So because we know the total pressure is 22 megapascals, and we've got 6 megapascals here for the partial pressure of Z, we know that all the partial pressures need to add up to 22. And so if we do 22 minus 6, we get 16. So we've got 16 megapascals left to share between the X and the Y. And because we've already been given the ratio of 1 to 3, this ratio carries through the entire way so from the initial, it carries through to the equilibrium moles, and then the mole fraction, and then eventually to the partial pressures. So that means that this 16 megapascals is actually shared between X and 3Y in a mole ratio of 1 to 3 as well. And so a quarter of it is X and 3/4 of it is Y. And so if we do 16 divided by 4, this gives us the partial pressure of X because it's a quarter of it. So we have 4 megapascals of X, and then we have 3/4 of Y. So we do 4 times 3, which is equal to 12 megapascals. And that's the partial pressure of Y. And then for C, calculate the value of Kp for this reaction under these conditions and state its units. So now we just plug in all our partial pressure numbers into our expression for Kp. So for C, Kp is equal to the partial pressure of Z squared, so that would be 6 squared, and over the partial pressure of X, which is 4, and then multiplied by the partial pressure of Y, which is 12, and that's cubed. And that comes out to be 5.21 times 10 to the minus 3. And now we need to work out the units. So again, we write out the units separately and then cancel. So we've got megapascal squared on the top, and then we have a megapascal times by a megapascal to the cubed. And so we can start cancelling. So I can cancel 2 off this megapascal and cancel this one at the top. So then we're left with 1 over megapascal squared. And so the units are megapascals to the minus 2 because we've got 1 over the megapascals squared. And then for D, when this reaction is carried out at 300 K and a high pressure of 100 megapascals, rather than at 600 Kelvin and 22 megapascals, a higher equilibrium yield of gas Z is obtained. Give 2 reasons why an industrialist is unlikely to choose these reaction conditions. So if we use a very low temperature, that means that basically the rate of reaction is very slow because there's less collisions per unit time, and so it costs quite a lot for the people running the reaction to be able to produce the products. And also for the pressure, if we use a very high pressure, then it's actually quite a big safety issue, and it also does cost a lot. So the answers are that a low temperature is expensive and a high pressure is unsafe and expensive. And for the temperature, you can also put low rate of reaction or slow rate of reaction. So the gaseous reactants W and X were sealed in a flask and the mixture left until the following equilibrium had been established. For A, write an expression for the equilibrium constant Kp for this reaction. And so what we do is we know that Kp is the ratio of partial pressures of the reactants to the partial pressures of the products. So we have the products on the top and the reactants on the bottom. So Kp is equal to the partial pressure of Y, and this is cubed because we have 3 moles of it, and we multiply that by the partial pressure of Z squared over the partial pressure of W squared multiplied by the partial pressure of X. And that's our expression. So for B, state one change in the conditions which would both increase the rate of reaction and decrease the value of Kp, and explain your answers. So first let's think about Kp, and we know that only 2 things can change the value of the Kp, and that is either change the temperature or the pressure. And that's because if we change concentration and use a catalyst, it doesn't change the value of Kp. And so we've only got 2 options. And first let's consider pressure. So pressure does change the value of Kp because increasing the pressure shifts the equilibrium to favour the side with the least amount of moles of gas to decrease the pressure. But it doesn't increase the rate of reaction. In fact, it doesn't change the rate of reaction at all. It just makes the equilibrium shift to either the left or the right to favour the products or the reactants. And so the answer must be temperature. And so let's have a look at the reaction. So we see that the forward reaction is exothermic, and that's because of this negative enthalpy change. So we know that heat is given out, so it's exothermic. And so if we increase the temperature, then what happens is that the equilibrium shifts to decrease the temperature. So So what happens when we increase the temperature is that the equilibrium works to decrease the temperature. And so it favours the endothermic reaction. In this case, that is the back reaction. And so there are more reactants formed because the equilibrium has shifted to the left. And so because there are more reactants which have been formed, that means that the value of the bottom of the fraction for Kp is much bigger. And so our value for Kp decreases. So the first thing to say is that when we increase the temperature, then what happens is that the equilibrium works to decrease the temperature. And it does this by favouring the endothermic reaction, favours endothermic and in this case that is the back reaction. So we know that equilibrium shifts to the left, and therefore we have more reactants, and so the Kp value decreases. And now we need to discuss why an increase in temperature will increase the rate of reaction. And that's because when we increase the temperature, we supply the gas molecules with more energy. And this is kinetic energy. And this means that the particles collide more frequently. So there are more collisions per unit time. And this also means that more of the particles, a bigger proportion of the particles, will have the activation energy needed for a successful collision, so to react. So a bigger proportion of particles have the activation energy, or an energy bigger than the activation energy, so they can successfully react. And so we have more successful collisions per unit time. And so overall, that means that we have a higher rate of reaction.